In this video we're going to look at how to construct a peak model for a carbon 1s envelope, and this is based on a set of measurements that include oxygen, 2 sets of sulfur and a couple of wide scans with a valence band, a couple of Auger peaks. And the idea is that we're going to use all the information within the data set to work out how to produce a peak model for these data. If we look at the survey spectrum and put regions on the oxygen, the carbon and the sulfur 2s, and then quantify based on these 3 regions, we end up with 1 sulfur to 27 carbon to approximately 4 oxygen. And that would be consistent with this model here for the polysulfone. There are 4 ring sets of carbon atoms plus 3, so that's 27 carbon atoms. There are 4 oxygen, 2 associated with the sulfur and 2 as ether, and then we have 1 sulfur. So the empirical expression here is consistent with the sulfone model that we're going to use to construct the peak model. When constructing a peak model for a carbon 1s spectrum, we need to consider how many peaks there are within this peak model, and we also need to consider the relative intensity and any shifts in energy due to bond state. So the first job is to identify, out of these 27 potential carbon atoms, we need to identify the different bond states that are equivalent. So for example, if we consider these as equivalent carbon within this polymer, then the carbon 1s from these will all appear at the same binding energy, and therefore we should expect an intensity that is proportional to the number of carbon atoms that we can identify in this common bond state. Similarly, we've got 4 carbon atoms that are bonded to oxygen, so these will be chemically shifted, and there should be 4 atoms for every 19 that we see in this carbon state. Similarly, we've got 2 for sulfur and also 2 that correspond to CH3 type bonds. So potentially there are 4 different synthetic components we need in the peak model, and 4 different offsets and a range of different intensities that will be determined by the number of atoms we identify in each one of these bond states. Before proceeding to the carbon 1s peak model, we first will investigate the anomaly here in the amount of oxygen. If we consider the number of oxygen atoms in this polymer, you would expect to see 2 in a single bond with carbon and 2 in a double bond with sulfur. So that means that in terms of XPS we ought to see 2 peaks of equal size and potentially offset in energy due to the different bond states. So looking at the oxygen 1s narrow scan measured using parsonage 20, we have a pair of peaks here, and they are in a given proportion. If we continue the measurement of the sample using parsonage 10, we observe that one of these peaks has reduced relative to the other peak, and at parsonage 5, although the energy resolution is improving, we can once again see that the ratio of these peaks has changed, and the same peak has reduced in size. So what we see from this is that the oxygen is not stable during the measurement process, and what we believe is there originally, after we've measured for a period of time, may have changed. Hence, when we look at the oxygen in the quantification, we shouldn't be surprised if we see less oxygen compared to the sulfur. Well, actually that statement needs explaining also, because if we look at the sulfur 2p, this is the characteristic binding energy for a sulfone. However, over here we can see a peak, a small peak that is looking more like a sulfide, and as the measurement is performed you can see the sulfide peak seems to increase with each measurement, and so it would appear that the oxygen is going away while the sulfur is being retained in some form and can be analysed as a distinct chemical state, but nevertheless the sulfur is still within the sample. We'll now move to construct a peak model for this carbon 1s. So the first thing to do is to define a background. We're using the quantification parameters dialog window and create a background. So this has come in as a U2 2GAR background, and you can see that it doesn't really represent the background very well. However, there's a U poly 2GAR background which is designed by 2GAR for polymers, and again this is a universal background, so it's a one size fits all, but nevertheless it does a better job of representing the data here. So at least for a first approximation we will go with this particular 2GAR background, and the reason that we've needed this is because there's this structure here that is related to the ring nature of this polymer. This peak appears whenever you see ring polymers in different shapes and different sizes, but nevertheless it's one of those indicators that you've got a ring within your polymer. Going to the components property page, we can now add synthetic components. And you see here we've got a line shape that has been entered, and here's the component peak. And if we just start off by having a full width half maximum about unity, and then we can copy this and paste, and then we'll move this peak so that we need for sure a smaller peak times in the ratio of 19:4, representing the oxygen 1s bonded to the carbon 1s. So this one here I'm going to indicate as having a CO type peak, and I think there should be 4 of these, so I'm going to say *4, and that will be used for annotation of the peak model. So let's actually add that annotation. So I'm going to say I want a formula, and I want it from the active tile, and we'll just say apply. So you can already see that we have a ratio of these two peaks just by accident is close to 19:4. So now add 2 more peaks, and I think this one here is going to be one of the CH3 or the sulfur peaks, and both of these ought to be half the size of the oxygen. So that's one. I'll copy that and paste, and that needs to be B star 0.5. So I have 2 peaks here. Let's zoom in so we can see it better. And this one here is going to be my CH peak, so I'm going to call that CH3. And this one I believe to be the CS. So there's no surprise, because I've introduced 2 constraints, that I've got 2 that are half the size of one and the other one is significantly bigger. So before we attempt to fit this, let's add some peaks over here. This structure that's associated with a ring of carbon atoms. So if I say create, I'm just adding peaks. I'll move them around. Just one more. I'll say fit. So having fitted these data, we end up with a peak model that is indicating that we have slightly less than the CC type bonds. So what we'll do is we will introduce another constraint. So here we have the large peak should be B times 19 divided by 4. And that gives us now the expected ratio. I'll take off the use RMS, and say fit. And let's have a look at the residual. So we're getting close to a peak fit that suggests that we've got a set of peaks. These are the main ones, these are all the satellite peaks. That these main ones can be constructed in the ratio that we would expect for this polysulfone. Let's just do a little bit of bookkeeping here. I'm going to set the component index to a non-negative value. And for the final set here, I'm going to say set equal 4. And then when I click here, you can see that I end up with all the same color for these ones, and I can, having given them the same component index, I just want to set the relative sensitivity factor to be 0 for all of these, with the net result that it's only reporting the component peaks for which a RSF other than 0 has been entered, so these peaks here. So we're now seeing a peak model that will represent, let me just display the slideshow again and go back to the original polysulfone description, that we've got 19 to 4 to 2 to 2. So this peak model would be consistent with what you'd expect for this polysulfone. And if I then add an annotation table, and we'll include in here the ratio and the offset, we can see that we've got peaks in a certain ratio, and we've got binding energies now to consider. So let's do a calibration, and we'll do it based on the energies that are assigned by Beamson and Briggs for a ether sulfone. So first of all, I've selected that carbon, that's the main carbon. I'll bring in its position, and the position in Beamson and Briggs is 284.7, and we need to shift region components and press apply. So we can now read off what these look like in terms of relative binding energies, and we've got, this is the ring, and then this is the oxygen bonded to carbon, that's 286.41. that's very similar to what you see for the ether sulfone, and the sulfur is the blue one, and that's 285.6. that's slightly shifted from what Beamson and Briggs suggest for the ether sulfone. And then we have something that is very close to 285 for the CH3. So there's a certain consistency here, at least in the binding energies, that have been derived from a peak model. So the next step would be to work on the line shapes and perhaps other parameter constraints to try and improve the quality of this peak fit in terms of a residual standard deviation, while at the same time maintaining the chemistry and the chemical relationships that we'd expect for this sulfone. And ultimately we will have a peak model that supports the assignment of polysulfone PSF for these data.